introduced me as Agustín. So I'm Asgeir Bjarnason, and I'm from the company Staroti that makes various sensors for ocean and aquatic research. But the topic that I'm going to kind of narrow it down to is related to biologgers, more specifically physio-loggers, and how they are being used to advance fish welfare research. So I'm a biomedical engineer, studied in Iceland and in Finland, and I specialized in medical instrumentation and signal processing. So I don't come originally from the fish field, but I've been working in that for a long time. I come more from the human side and actually all kinds of animals in my work with Staroti. So I've been working with implantable measurements since 2008. And in over 150 animal models. I specialize in electrocardiogram and heart rate measurements, temperature and acceleration. And I've been the lead designer of Staroti implantable product line since 2012. Just want to kind of give you a couple of slides about the company. So the company predates me quite a lot. Founded in Iceland in 1985, and in 93 it released its first product, more or less. There was some smaller, let's say, attempt before that, which was a so-called archival tag. It's a temperature and depth sensor that was attached to fish to try to locate Atlantic cod for the commercial fisheries. And in 23, a side project became implantable loggers and for mammals, and this was used and is used quite a lot in virology, laboratory research, domestic mammals and others. And then when I had kind of finished my studies, I came to work for Staroti and developed this what we call physio-logging or bio-logging product line. It measures heart rate, temperature and activity, and we released the first sensors in 2013. So we've been over 10 years supplying this. But the company, they do, let's say, different things, as I was introduced earlier. But my focus is going to be on fish, obviously, and the physiology, and not really on any like environmental equipment or measurement devices. Okay, so what is a biologger? So a device tracking biological data for scientific research and monitoring. So this can be environmental data as well. This can also be tracking the location of the fish. So this kind of includes quite many things, but usually it means that it's a device that is attached on an animal. And then a subgroup of that would be a physio-logger. So that's a device that is monitoring the physiological parameters for health or research purposes. So maybe something closer to, you know, like a wearable device that we are used to in humans, measuring heart rate and activity, giving you a health indicator, so to say. And it is pretty hard to get anything or like a proper signals externally from a fish or from an animal, especially if you want to measure for a very long time. You can, yes, measure, for example, activity, you know, and as a proxy of behavior and tail beat frequency, etc. But it's very hard to get anything, you know, from the heart, for example, the electrocardiogram or blood pressure, etc., without implanting the device or putting it in a vein or something. So what we do is, like, we have these sensors and they are implanted in the fish. And to measure the heart rate, they need to be implanted pretty close to the heart of the fish. And there are several papers that have been published using these. Most of my talk is going to focus on Atlantic salmon. And as Alfredo correctly pointed out, it's not the biggest, let's say, or the fish that is produced in biggest quantity, but it is, however, probably the fish which the greatest research has gone into salmonids and especially Atlantic salmon, and it's also the group that probably spends the most to try to improve welfare and the aquaculture practices. So the data that you can get out of this, in short, looks something like this. So here you have a fish. So each color here is indicating different fish, and then you have the average in the black. The fish is implanted. There's some recovery phase where the heart rate is elevated. You have a diurnal signal or rhythm, let's say, in the heart rate, and then you have some stressful event. In this case, it's an artificial stress event where you lower the water level in a tank and you chase the fish to elicit the maximum heart rate response. The fish recovers over about 48 hours. And in the bottom here, you can see the activity profile. So after the surgery, the fish is actually quite active. Then it's with quite low activity. And after it's been chased, the activity is quite high. You can actually see that the activity lowers when the water level in the tank is lowered. So, quickly, how one would implant such a sensor. So this is obviously a pretty big task if you're talking about a whole cage of maybe 70,000 or 100,000 conspecifics. So you would obviously be just implanting a subset of fishes to give you kind of like a proxy of what's going on inside the cage or the tank. So you need to anesthetize the fish, and you need to make a small surgical operation on it, which can take maybe 3 to 4 minutes, but the anesthesia part can obviously take longer. So the sensor is placed inside the fish, it's sutured close to the heart, then you suture the wound, and you release the fish back in the tank. So what I'm focusing on is a single channel ECG. So to measure heart rate, we have a electrocardiogram signal that you detect the QRS waveform, and birds, mammals, and fish, they actually have surprisingly similar ECG signal. So we can apply methods that are developed for humans with small customization to process data recorded from fish. And then we have also 3-axis accelerometers, and in our case, we are mostly using them to measure activity, gross motor activity. We call it external acceleration, which is more like an overall activity. But that's triaxial data where you will have so-called static axis and a dynamic axis, and we try to eliminate this static axis, and focus on the dynamic axis to calculate metrics, and some of them are called, for example, vectoral dynamic body acceleration or overall dynamic body acceleration. You can also, as you can see from the raw data, extract signals such as tailbeat frequency or respiration, depending on how the sensor is placed. But that would be a little bit more specific, and you would need to look at the more raw data stream rather than a calculated processed stream of data, which in our case we are usually doing. You can do both with the sensor. To kind of finish off the background, I want to make this connection with smartwatches and fitness trackers, since that is something that has been growing exponentially in the later year. And there are hundreds of million devices produced every year, and most people have. And kind of show how in the human science, like those smartwatches and fitness trackers, how they have been changing over time. So the current focus in those has shifted from, let's say, measurement activity and movement. So that was more like step count, measuring GPS coordination, where you're going. And a lot of them have been adding physiological measurements. So they have been adding relevant changes in physiological variables such as resting heart rate variability, oxygen saturation, monitoring your nighttime, let's say, physiology, resting physiology, to give you more of a health approximation or some kind of index. And this is interesting because it opens up also a lot of applicability to take that and those models that are maybe being made for human and trying to kind of extract ideas to put into something for fishes. Another thing which is also important, and one could give, of course, a whole talk about that, is the case of when you have to kind of like understand your data and calibrate your data. So yes, you have human, everything is developed, maybe most of the theory is developed based on humans. Some of it has been applied, of course, heavily in like laboratory animals such as rats and non-human primates. But can you take it at face value and just apply it to a fish and not maybe Atlantic salmon, but any fish type? So that's where things can often get tricky. So usually in humans, what you're using heart rate to is that you're trying to build a very strong relationship with oxygen consumption, so the energy, let's say, consumption, and you try to make a linear relationship. So the cardiac output is heart rate versus stroke volume, and in fish, that relationship is actually a little bit more or less linear than in humans. However, in fish, how you would establish that kind of a relationship would be to measure for example, the standard metabolic rate and then the maximum metabolic rate of fish. So you put fish in a swim tunnel and you measure the respirometry there. And then you have a heart rate sensor and you're calibrating the heart rate of the fish under different temperature conditions, and you're calculating it under different, let's say, swimming speed condition, and trying to find which heart rates represent, resting versus, maximum exhaustion. And here you can see fish in a swim tunnel, and usually you have two maybe types of in Atlantic salmon, at least, you have two types of swimming conditions. So you have the steady swimming one, which is low swimming speed, and then you have the non-steady swimming. So I'm telling you this because I'm going to show you then some real life examples where these two metrics are used to quantify, let's say, behavioral states of a fish. So there are validation studies with our sensors where you have activity parameters and swimming speed, and usually they use this, let's say, variation of the activity to define when it's more or less in the steady swimming condition versus burst swimming, where these the variation metric, let's say, increases. So above 250 is usually used as a cutoff to define steady swimming versus burst swimming. And this has been corroborated with other papers and then other species as well, such as yellowtail kingfish and sea bream and others. Okay, so we can measure heart rate. Okay, and we measure the swimming speed, and we measure it at 12 degrees, like here. And so this is similar to like a VO2 max, where a human goes on a treadmill until it's exhausted, and you calibrate heart rate and you calibrate the respiratory, the metabolic rate. So here you can see the fish reaches kind of like exhaustion. So 100 centimeters per second, and the heart rate is around maybe 85 at 12 degrees. And in this study, they recover the fish, and what they see is that the white dots here, or the circles, is the fish prior, let's say, to the study. So it has diurnal cycle This light gray is 8 out of the 12 fish that were swum. They recover here in about 36 hours. But 4 of the fishes, they never recover. So the heart rate keeps being high, around 80 beats per minute. It becomes very irregular, and they die after about 100 hours, after about 4 days. So this is interesting. And then, yeah, so this is just kind of like a further overview, another study, a quite recent one, where you have, again, let's say a replication of the data I previously showed you, but this is in a sea cage. So they have, they try to kind of replicate a stressful event in a sea cage and measure increased heart rate and activity. And one thing that is always important also to keep in mind is that you need to have sufficient amount of fishes to be able to, let's say, quantify a true response. I mean, you can never be just looking at a single fish, because what we see here is, I mean, the activity is quite homogeneous over the whole group. But what we see with heart rate, for example, is that there are fishes that have, like this one here, have very high rate. Some of them have irregular rate, but when you kind of look at the average of maybe 10 to 12 fishes or more, then you start to see a better image. So that's kind of maybe one thing that is important, is that you need to obviously be looking at the yeah, a certain group. Okay, so how can we kind of now put all this information into like a real case, a real live example? So here's an example of that. So this is fish that was tagged in Newfoundland in July in 2019. And it's double tagged. It's tagged with temperature, heart rate, and activity sensor inside the fish, and then a temperature and a depth sensor outside of the fish. So what we're looking at here is pretty much the water column indicates, which is recreated through the tag data, so the temperature and depth data. So you have a heat wave. You have surface temperatures reaching, around 20, 21 degree here. And then you have the daily and nightly averages of the fish, the dotted line and the solid line, during this heat wave. So, and it's an extensive heat wave. I mean, we're talking like 20 days of heat wave. And the fish keeps kind of going deeper and deeper in the cage to let's say, reach colder water. So here we can see an overview of the data. So we have daily is the open circle, and nighttime is the dark circles. So you have fish, it goes down. At this first indicator, it means that they withdraw feed. So they withdraw feed to reduce the fish coming to the surface. So kind of trying to keep it down, to keep it in temperatures that are lower, because we see that there are definitely like, temperatures below 10 degrees that it can kind of find, maybe below 10 meters. So the internal temperature of the fish is actually not so high, although it's still reaching here maybe about 17 to 18 degrees. The heart rate is kind of quite high here, and then it lowers, and there's a strong relationship between heart rate and temperature. But then we can see this part number 2. So at part number 2, there is mass mortality happening. So in this case, it was about, I think, 70% of the fish that died, but we're looking at data from fish that didn't die. And so what we can see here is that, I mean, the fish during the daytime goes very deep in the cage. The temperature is between 14 and 15, internal temperature of the fish, but the daily heart rate is reaching very high levels. It's reaching close to a 80 daily average. Heart rate variability, which is pretty much the metric of how regular the beats of the heart are, is very low. So this usually indicates a very like strong sympathetic response, or like a stress level. And what we see from the activity data is that the activity data is high, and this is the non-steady swimming metric. It's also very high. So the fish is struggling a lot during this time. So this is kind of like an indicator of something in the environment is happening, and the fish is let's say the physiology of the fish is responding in a certain way. Now this was a pretty dramatic event there, and it was called the Mowi meltdown. In 2019, when this study happened, 1 in every 3 fish died in Newfoundland and Labrador. In 2020, 1 in every 5 fish died. So when we're talking about welfare, I mean, we're also talking about, we're talking about the welfare of the fish, but we're obviously talking about, survival as well. And I mean, in some cases, this is not so dramatic, and I think in Norway, for example, they have it, it's much lower, the mortality. But in some countries where the environmental maybe pressure is higher, there can be large mortalities. Okay, so I just briefly mentioned, that there's a relationship between heart rate and temperature, and you can see it kind of here. So there are studies that have been close to a year, so you're measuring the heart rate, temperature, activity in the fish close to a year, and then you can easily plot those kind of relationship for not only for a tank fish, but for a real fish kept in a sea cage. Another thing related with that, real life story is there was a report made about that mortality, and they said, well, the heat wave killed all the fish. But what we could kind of see from the data of the sensors is that the physiology, the fish should handle, let's say, higher temperatures, and in laboratory, etc. They have been showing that very clearly, that the fish can handle maybe up to 22-23 degrees before it 50% or more is dying. So there's probably something else that was also going on there, and there were some lice cleaning activities happening in at least in some of the cages, and other papers have shown, for example, that you have this kind of like a cumulative effect of multiple stressors that limit the cardiac scope of the salmonids. So if you do, let's say, you do like a stressor, and then you give it maybe 10 hours of recovery, you do another stressor, the baseline of the heart rate will keep on increasing, and the scope that the fish is able to increase the heart rate lowers. So what can also be happening in this kind of a case is that if there's a lot of maybe handling that has been going on, or something went wrong in the handling, and you can see that the stress level of the fish is unusually high, then obviously like environmental pressure such as heat can definitely have a greater impact, and maybe the fish is not able to cope with those kind of quick environmental challenges, or when you see, I mean, obviously the farmers are taking best practice, but this can still help to kind of evaluate the situation, in theory at least. Okay, so there are many examples that one can make, and a lot of correlations. And I mean, this is like, okay, it's simple, but in reality, I mean, it's not simple at all. So there are many papers that have come out and studies using these sensors, and then there are a few papers that are doing a correlation, let's say, with plasma cortisol. So you're doing some crowding, you're doing, let's say, a controlled stress event, and you're measuring plasma cortisol at different levels in the group, measuring heart rate. So it's like pretty good pretty good correlation that has been shown in that. There are some studies coming out where they are looking at water quality, such as nitrate or nitrogen levels over a long time. So that would be an example here. I mean, obviously, if you want to use heart rate as an indicator of such measurements, you need to be able to control a lot of other parameters to kind of make sure that those are not the ones increasing your rate. Brand new paper last week looking at behavioral stress test in bolt and shy trout. There are some stuff on feeding effect and quality, papers on environmental enrichment, and then there's a lot of work being done on different species. So obviously you say, okay, all this works and doesn't work for Atlantic salmon. What about all the other aquaculture species? You know, the Mediterranean species, sea bream, sea bass, tunas. You know, what about the carps, the tilapias, catfish, etc. And that's where and I think that also kind of answers a little bit the questions that was proposed with the imaging. You know, that you can say, okay, I'm a company, like I have it all figured out with like 1.5 kilo salmon to 2 kilo salmon. But what about the weight also, or size? What about the small ones, the larger ones, and what about different species? I mean, there's a lot of work that kind of has to be done, I think, in the domain to figure out all this. Okay, so what's next for us? So everything that I've presented here, and there's about 65 papers that have been published using these in fish and majority of them in aquaculture. However, those are all loggers. You need to retrieve the device to be able to read out this data that I was showing you. So obviously that's in a commercial application that can be very difficult and challenging. So what we have been doing, and we ran one study in Newfoundland and one here in Spain, in Mallorca, with Pablo Archivala, who's here on the right, is to have a acoustic transmission of data. So this is a meager here, Corvina, that we implanted in a sea cage just for our experimentation. So this transmits the data. So you have here the temperature and heart rate. So first the fish is put in a kind of a concrete pool, and then it's put in a net pen, and then you have a receiver that can give you information about what's going on. One thing with that, of course, is that if your receiver is gone, like here, you don't get any data. But with our loggers, you can actually record also what's going on. So here we have that period where they were kind of doing some stuff in the cage, and they removed all the receivers, etc. So yeah, I mean, you can see kind of an increase here in heart rate. So yeah, so that was kind of all I wanted to say, and to kind of give you at least a bit of an idea of how one can use those kind of sensors to yeah, let's say like individually track fish. So I think that can corroborate a lot of the other, let's say, external solutions, that have been discussed, which are obviously more perhaps practical on the large scale, but this can supplement very nicely those kind of data.